Welcome back to another video that adds to our discussion of recursion in SQL. This is chapter 6 of the Advanced SQL lecture. What we will discuss in the following minutes will lead us to the limits of the notation of recursive CTEs. We will encounter a situation where we would like to use one particular syntax in defining our queries, but restrictions on recursive CTEs will forbid this particular formulation. There are ways around it, very elegant ways around that, but this will lead us to a general discussion of what syntactic restrictions are there on recursive CTEs. But before we get there, let's discuss the use case that we are considering in this video. And this is the encoding of cellular automata or CAs. Cellular automata are finite state transition systems that you can use to model a variety of phenomena out there in natural sciences, in social sciences, in biology, physics, chemistry, in math. It's really mind-boggling what you can map onto cellular automata. You will find entire internet communities devoted to the exploration, development, discussion, implementation of cellular automata. Really super powerful and super versatile formalisms to capture dynamic systems. In these systems, you are talking about cells, and cells have a state that can change from generation to generation. All right, cells are organized in n-dimensional grids. N, of course, will be 2 again in our discussion here regarding the slides. But, well, cells could be oriented in a 3-dimensional space and then have neighbors that are just left or right, in front or back or top or on the bottom or on top of these cells. And that's a generally a very important consideration. What is the neighborhood of one particular cell? Of course, in the neighborhood of one cell, we find other cells. And the cellular automaton will have rules that describe how these neighboring cells impact our cell in the middle and how that cell in the middle impacts all the cells in its neighborhood. And the description of these rules gives the whole system a very unique dynamicity. And we will see that one can encode all kinds of different things with cellular automata. We will look at 2 different applications here in the course of this lecture, but as I told you, the possibilities are just endless. Okay. Right. So what we will discuss in this course is actually 2 different flavors of cellular automata. The first flavor on the left here is what we will describe in this video. And it's also the more straightforward variant, at least as it relates to our implementation of CAs in SQL. This is the type of cellular automaton in which a cell C is influenced by its neighborhood. All right, so what the neighborhood of a cell actually comprises is more specifically defined on the next slide. But well, any C will be surrounded by neighboring cells. The state of these cells, maybe the presence or the absence of these cells, of these neighboring cells, will influence the state of our cell C in the next generation of our cellular automaton. So in general, these cellular automata change state from generation to generation in a discrete fashion. So all of the cells are in state 0 first, then on the next state, in the next generation, we will decide the state of each cell based on the influence of its neighborhood, at least for the type of cellular automaton described here on the left. The type on the right is different in the sense that here the cell C has a more active role. It influences all its neighbors. Okay, so one can define and simulate completely different systems with these types of CAs. What we will do in this course is to define and simulate and then play with Conway's game of life would be probably one of the more prominent applications of cellular automata in general. This is of the first type, in which a cell is influenced by the state of its neighborhood. All right, indeed, the neighborhood determines and defines whether a particular cell comes alive, stays alive, or dies. That's Conway's game of life. The other application that we will consider is the simulation of fluid flow in a very simple, very simplified scenario, where we will try to simulate different types of energy, potential energy, kinetic energy, and use that to simulate how fluid flows in a particular container. Right. So, but one thing after another, our focus is entirely on the Conway game of life style of CA's, the left-hand style type. And it's also the more straightforward one, right? The second is more involved. We will cover that, and it will be easy in the end, but it takes some preparations to get there. All right. So how about this cell neighborhood? Right. So cell neighborhood is actually can be very flexibly defined. Every CA could define its own notion of neighborhood. So how far will a cell actually look, or how far will the influence of particular cells reach when they influence their neighborhood? Well, this is very flexibly defined, but what you will often find is two types of neighborhood: the so-called Moore neighborhood and the von Neumann neighborhood. All right, and we will look at the Moore neighborhood in our application of game of life. In the Moore neighborhood, there is one particular cell, the cell in the middle, the dark cell here in the middle. That would be our current cell C, and the neighborhood would be the 8 cells around this dark cell, of course in a 2D grid. In a 2-dimensional grid, we would have 8 neighbors that would be able to influence the black cell, that influence and determine the fate of the black cell in the next generation. There's also the von Neumann neighborhood, where you see that only the 4 immediately orthogonally adjacent cells influence the fate of the black cell, unless we consider the extended neighborhood, which could reach to these smaller depicted cells here, and we could even reach further outside. But this is all defined by the particular CA application that we are considering. Our focus will be on the Moore neighborhood of the definition of neighborhood. All right. Our encoding of the cells themselves in such a 2-dimensional grid and the cell state will be super simple. We will be talking about a table grid that locates the cell in a 2-dimensional XY position, and then a column cell inside that table that will just define in some CA dependent sense what the current state of the cell is. You will see that in the application of game of life, all that interests us is whether the cell is alive, and that would be a 1 in this particular cell or table cell, or whether the cell has died. That would be a 0 in this table cell here. Okay, so this is all the setup we need. We could now already look into details of how could we write a query that explores the neighborhood, the 8 cells around this black cell. Well, probably we would have to access these 8 cells to read their current state, perform some function on this state, and the outcome of that function would determine the outcome, the fate of our black cell. Okay, so let's look at how SQL code could look like, to implement this neighborhood influence. Right. This slide looks easy enough, but let me warn you, it's actually describing a non-solution, a solution that we cannot use in SQL because of syntactic restrictions that are in action when we talk about recursive common table expressions. All right, so let's assume that we are inside our CA implementation, and we are actually looking for ways to implement the Q loop query. the iterated query that examines the current state of the grid, and for each cell C tries to determine what the next state of that cell C would be. Maybe this would lead to a recursive common table expression of this shape. We would have a recursive CTE that computes table CA, cellular automaton, and CA would of course store for each cell at a particular location its current state. All right, so this is something that we can rely on to be present already when we enter our Q loop query. That would be the current state, the most current state of our cellular automaton. If we now want to explore the neighborhood of each cell C, so let us grab one cell C out of the current state of the cellular automaton, and then let's grab all other cells in the neighborhood of CA. Then we would probably have code that looks like this. Well, we would iterate over CA to get hold of all cells C, the black cells in the previous slide of our grid, and then would access CA, the cellular automaton, again to explore all the cells N in the neighborhood of C. To make sure that N is indeed a cell in the neighborhood of C, we would have a where predicate here that identifies, in this case, the Moore neighborhood of C. All right, so if you look closely at this expression here, at this predicate, this would exactly admit those cells N that are in the Moore neighborhood, one of the 8 cells in the Moore neighborhood of cell C. Okay, once we have identified such a neighbor of C, okay, we would then be ready to compute the next generation of our cellular automaton. So in the next generation, there would of course be a cell at the location of C, so we would just keep the X and Y coordinates of our cell C, but the state of that cell C might be changed. So this is the expression that would compute the new state. We are being very abstract here, and that expression would be just some function f that we are not looking into here. At this point, it's just not interesting. Later on, when we do Conway's game of life, we will have a very concrete f here at this position. In this abstract form, well, that function f that computes the new state would look at the current state of the cell, which is just c.cell, and it would look at some aggregate of the state of the neighboring cells. As you can see, this is some abstract aggregate. Maybe it's summation, maybe it's a maximum, maybe it's a user-defined aggregate that we have to define. This aggregate would have access to the 8 cells in the neighborhood of our cell C, would compute some aggregate value, and that could then be used to, together with our current state of the cell, to determine the new fate, the new state of the cell. All right, all of this looks really well organized and simple, but indeed it would be illegal to write this particular SQL code, and the reason is here. It's the second reference to the recursive table. Okay. So there's one reference here, and we always had that. Of course, QLoop has to access the state of the last iteration, but the QLoop query may only access this particular state once. You may not access it twice or 3 times or whatever. This would be the equivalent of a nonlinear recursion in SQL. And for performance reasons, just for performance reasons, the SQL standard forbids multiple references to the recursive table. Okay, so this is what I'm referring to down here in this bullet point. Indeed, the SQL standard forbids multiple references to the recursive table. Okay, bother. This is something that we have to work around or circumvent. Right, before we do that, let's take a step back and look at all the restrictions, all the syntactic restrictions that are in place on the QLoop query. So there are some. The next slide will list them all. And well, we haven't encountered them so far. Well, we almost didn't encounter them so far. So that's an indication that you can, of course, Right, very sensible, very useful recursive queries in SQL, but now and then you will encounter the syntactic restriction, and then it's your task to work around that. There are many ways around these restrictions, so let's not be shocked when we look at this particular list. All right, so with recursive is indeed syntactically restricted. Let's assume that T is the recursive table that is being defined by our recursive CTE. So T would be CA in the example on the previous slide. So this is something we probably expect. In the base case query, we may not access the recursive table. The base case query determines the first initialization for this recursive table T. So we expect T to not be accessible in the base case query. That's fine. There may only be a single reference to the recursive table in QLoop. That implements linear recursion. I've just mentioned that. Right. We may not refer to T in subqueries. Subqueries inside the from clause are okay, and references of the recursive table inside subquery in the from clause would be fine. Subqueries in the where clause, subqueries in the select clause may not refer to the recursive table T. The recursive table may not occur in intersect or except invocations, so it may not be the left-hand or right-hand side of an intersect or except operation. T may not occur in outer joins, at least not on the nullable side of an outer join. So in a left outer join, it may not occur on the right-hand side, for example. There may not be in QLoop, there may not be aggregate functions. We may not use aggregate functions in QLoop, which comes as a shocker. But let me tell you, we may use window functions inside QLoop. We may not use order by, offset, or limit in QLoop. Right? This often is of no further concern because ordering stuff is indeed almost always an operation that occurs at the top level, and we often find such constructs of SQL in the post-processing query of the recursive CTE only. Right. So all of this sounds very restricted. And indeed, I think my personal opinion is it's a pity that many of these restrictions exist. They exist to allow systems, to enable systems to perform certain optimizations on the evaluation of QLoop. In particular, these restrictions enforce that QLoop is a distributive query. Right. QLoop being distributive means that we can perform the QLoop computation on a table that looks like this. A table T that has some rows small t added to it. Well, we could evaluate QLoop in this particular fashion. We could just look at the value of QLoop at t. Maybe this value has already been computed because t is the table, the recursive table of the last iteration. And we would only have to compute QLoop on the new rows, the few new rows that have been added to our table T here. And of course, this would be efficient because we would hope that this set of new rows is indeed very small. In the slide here, it only contains a single row, small t. Well, it might contain more rows, but hopefully very few rows. We could assemble the entire result by looking at a result that we've already computed plus some small delta. And well, this is one particular optimization opportunity that RDMSs could use and could exploit. Practice tells us, and looking at current query optimizers tells us, it's just not being used. This cool algebraic property of QLoop is just not being exploited by the systems, and instead this expression is computed in the regular, non-fancy, non-optimized fashion. This also means that all of these limitations are in place. Well, this limitation I think is a no-brainer, but all of these limitations are in place and they are not being exploited. And well, the system could very well operate in the presence of constructs like this in QLoop. The standard forbids it. Most systems, and PostgreSQL is no different, forbids it. Therefore, we will see workarounds around these limitations. Very elegant workarounds actually, which also hint at the fact that PostgreSQL is perfectly capable of performing recursive computation with QLoops that have these query features. But okay. Right. So we were talking about the computation of the neighborhood of a particular cell, of the Moore neighborhood, for example. And I told you that the version on the slide, on the prior slide, is actually no option. What would be an option, however, is the next version, which is based on window functions. And I think it's even the more elegant and more readable version and more flexible version of the code that we have seen on the previous slide. So let's recall again. We were inside our QLoop query, and we had the task of exploring all the cells C in our current cellular automaton. And of course, we would like to explore the vicinity, the neighborhood of C, to also compute the next state of C. Right. So what we will do instead now, instead of the self join of CA with itself, we will use a construct like this. Okay. You will probably recognize the F and the AG here. We use these to encode. We use these to encode the behavior of the CA, of the cellular automaton, right? So we use this aggregate to abstract from the specific way in how the CA reads the neighborhood and then processes the state of the cells in the neighborhood. And we use the function f to abstract from the details of how the state of the current cell and of how the aggregate state of the neighborhood is being used to compute the new state of C. Right. So what defines the neighborhood? What defines the reach of this aggregate actually? And the answer to this is, well, we will be using a window function that defines a particular frame, and we make sure that the frame only admits rows in the neighborhood of cell C. All right. How would these frames look like? Well, these would be particular frame definitions for particular neighborhoods or subsets of neighborhoods that interest us. So you better read this slide in columns. So let me draw the columns here. All right. Okay. So if the black cell again is our current cell C, to access the immediate neighborhood below and above C, we could use this particular window frame to do just that. Well, we would partition all the cells in the grid by the x coordinates, which would define, of course, as this vertical stripe around our cell C. Okay. We would then even order the cells on this particular horizontal stripe by CY. You see that, well, if this is the location of our black cell at x1 and y1, ordering the rows in this vertical stripe by y would order them in a top to bottom order. Okay, so we even have a ordered or very well sort neighborhood. So this would be the first cell in the neighborhood, this would be cell C, and this would be the second cell in the neighborhood, in this vertical neighborhood. All right, to make sure that we are not looking at the entire stripe here, we would then be using rows between one preceding and one following restriction, which would indeed cut this vertical stripe at this and at this particular point. So indeed, the neighborhood is constrained to the immediate neighbors of our black cells here. All right. The window, the frame that we are defining is exactly this window of cells, you see that the cell C itself would be included in there. If this is not what we need or what we want, if we only want the cells in the neighborhood of C without C itself, we could use this modifier to frames. We haven't talked about these modifiers when we were introducing window functions, but it's there. It's there in all modern implementations of window functions, and it's there in PostgreSQL, for example. From that window, we could exclude the current row, which is the row C itself. So we would just delete this occurrence of the row in the window, and all we would left with is the vertical neighbors, the immediate vertical neighbors of our cell C. Right. We could, of course, define extended neighborhoods by just adjusting these two literals here, and thus have true flexibility in how we define these windows. So that would be the vertical neighborhood of our cells. We could, of course, define the horizontal neighborhood using the same trick by just using a frame that partitions everything by the y coordinate. That would be horizontal neighborhoods, ordering this stuff by x. Okay, looking at the immediate and preceding and following neighbors, and that would define the horizontal neighborhood that we were looking at. We could even define diagonal neighborhoods by using this expression here as a partitioning criterion. If you look at the xy coordinates, again, they are reproduced on the left-hand side here. If you look at the xy coordinates of the cells in this snippet here, then the difference of the x and y coordinates is 0 for all of the cells in this diagonal. All right, right. It will be -1 for all the cells of this diagonal. It will be +1 for all the cells in this diagonal. So partitioning the cells by this difference will identify diagonals in our grid. Again, we could order the rows in on these diagonals. If we use this as an ordering criterion, we would order the rows in this particular fashion. All right, and then looking at one preceding, one following would of course define the window frame, and so on and so on. So we would have horizontal, vertical, and two diagonal neighborhoods that we could all identify using window frames in a very elegant and very flexible fashion, I would say. And as you can see, in this formulation of the entire query, we only access the cellular automaton, the recursive table, once. This would be fine according to the SQL standard. We are also using window functions, which again would be fine from the viewpoint of the SQL standard. So this would indeed be a solution to very flexible neighborhood access in such grids. All right, so I think now all the basics are there. We could now use this to define Conway's game of life. So Conway's game of life indeed is performed on a two-dimensional grid of cells. And well, the cell state of these cells is very simple. Either they are alive or dead. So their state would be 1 or 0, right? Now, how would the next generation of cells be computed in Conway's game of life? Well, we would just count the neighbors of the alive neighbors or the dead neighbors in the vicinity in the Moore neighborhood of C, and then derive the state of C in the next generation just from this neighbor count. Right. So let's see, if our cell C currently is alive and there is less than 2 alive neighbors in our neighborhood, then that would mean that C dies from underpopulation. So a solo C that is really surrounded by too few alive neighbors would die from underpopulation. So the next state of our cell C in the next generation would be 0. Okay, so all of these rules are read like this. So if C is alive and well, the number of alive neighbors in our Moore neighborhood lies between 2 and 3, then everything is fine and our cell may live on. if C is alive and the neighborhood is just too busy. If there are more than 3 alive neighbors in the neighborhood, well, then we would die from overpopulation. All right. If C is dead and the vicinity, the Moore neighborhood, includes exactly 3 alive neighbors, then that would be considered ideal living conditions for our cell C, and C indeed comes alive, or it will be reproduced by its cells in the Moore neighborhood. These are the super simple rules of Conway's game of life. Looking at these rules, you may think that no interesting dynamic behavior can arise from these rules, but thinking that we would be very, very wrong. You can study and encounter all kinds of cool dynamic, periodic, or chaotic behavior in cellular automata, these two-dimensional grids that are defined by these rules of Conway's game of life. Okay, so this Conway's game of life is indeed one instance of a cellular automaton where the state of the neighborhood influences the next generation of cell C. So all the cells in the neighborhood, they induce the new state of the cell C and influence cell C. C is not influencing the state of its neighbors. So indeed we are looking at the cellular automaton of the type that we would like to consider in this particular video. By the way, John Horton Conway only died a few weeks back. He was one of the great minds behind, or the early minds behind the entire sub-community of mathematicians that were studying cellular automaton. All right, so those of you who have already seen game of life grids or game of life dynamic patterns may probably recognize some of the more notable patterns that you see now and then in these two-dimensional grids. These are notable because some of these patterns of cells, so indeed such a black circle indicates a cell that is alive, such a small dot here indicates a cell that is dead currently. Such patterns are notable because they reproduce from generation to generation and are stable. If we do not influence these patterns from the outside, they will reproduce from generation to generation and will just continue to exist until eternity. There's other patterns which are much more dynamic. These patterns actually oscillate, so they switch between two possible states between adjacent generations. So this, for example, is a so-called rotor that is horizontal in this particular generation, but will be vertical in the next generation, only to return to its horizontal state in this generation, and so forth. All of these are oscillators of period 2, so they come back to their original state after 2 generations. There are other oscillators, much more complex oscillators, which have larger periods. And then there's the spaceships which actually travel across the grid. So I think I brought an example with me where we can see how these spaceships indeed travel across the grid. So they deform, move through the grid, and then at one particular point take their original shape and form again before they move another step through the grid. It's really super interesting to observe. So that we can play with this, let's quickly implement this in SQL. How would the SQL query look like that implements this behavior of this cellular automaton? All right, well, to implement this game of life cellular automaton, we would use a recursive CTE, and the recursive CTE would compute a table live, okay, with 4 columns. In the first column, we would just write the protocol of the generation that we are currently considering. Probably we would start with generation 0, and with each iteration of the recursive query, the Q loop query that I've reproduced here, generation would be increased by 1, as you can see here. Okay, X and Y, of course, encode the location of the cell, and in the query, if we are looking at the current state of the automaton, and look at one particular cell L here inside the grid, you see that the location of L will not change. So in this generation, L is at coordinates X and Y. In the next generation, it will be at the same coordinates. So cells are stable in the sense that they do not change position. They may change state though. Okay, and to compute the new state, you see that this is a rather large conditional expression here, but all it does is compute the new value of column cell. So that would be the new cell state, right? So we expect the new cell state to depend on our own state, right? Which is what we have here. L.cell is our current state. And we would expect it to depend on the state of the cells in the neighborhood. And this is actually exactly what we explore here. We would explore the axis or the horizontal, the vertical, the diagonal in one and the diagonal in the other direction. All of this together would explore the entire Moore neighborhood of our current cell L.cell. Okay. Well, in Conway's game of life, we only count the number of alive cells. So all we have to do here is indeed sum up the cell states of all the cells in our neighborhood. In all, this parenthesis here will give us the neighborhood count, the count of cells that are alive in our neighborhood. Perfect. So this is all we need to implement the rules of Conway's game of life. We've got our own state. We've got the count of live cells in our neighborhood. This is all we need. We call these C and P here in this comment. And you see C and P values here in our conditional. So if we are alive and there are 2 alive cells in our neighborhood, then we may live on. If we are alive and there are 3 cells in our neighborhood, we may live on. Okay, so these are the ideal living conditions. Well, if we are currently dead, bother, and there are exactly 3 neighbors alive in our neighborhood, then we will be alive in the next generation. In all other situations, unfortunately, our current cell L.cell will die. Okay. So I think this would be it. This would be the entire encoding of Conway's game of life. All right. So I brought this file gameoflife.sql with me, and it contains an implementation of the dynamic behavior of the cellular automaton, and of course it contains a representation of the initial world, the grid of cells that we start from in our simulation. Let's create this initial world in the beginning here. So let's create the table that will hold it. And as you can see, this table is in a format that we have used so many times already. It's this row-based, ASCII-based, textual-based representation of 2-dimensional grids. Of course, these are alive cells. As you can see, we are having a few interesting forms here. This would be one of these rotors, which is horizontal in this generation, but will be vertical in the next generation, right? And this is one of the spaceships. You will see that it will travel from the top left here to the bottom right. This is one of the more complicated spaceships. It will travel from the bottom right to the top left. I think they should collide somewhere here in the middle if they continue to move. All right, so let's load this particular table here. And then let's check that we have read it correctly. There you go. This is the representation of 2-dimensional grids that you've seen so many times already in this lecture. Let's disable that for a reason. Okay, here are some notes on the neighborhoods that we've already explored on the slides. And here's our implementation of the live automaton. This is just the code that you have seen on the slide. What you find here is the Q0 base case query, which will simply read the ASCII-based world representation and convert it into representation where each cell is located at X, Y coordinates. That's all that's happening here. I've embedded this conversion into the Q0 base case query. All right, This is the dynamic behavior of the cellular automaton, and we have seen that already. What you will also see is the definition of the windows that define the horizontal, vertical and diagonal neighborhoods around our cell L. Alright, so these are just copied from the slide that was introducing the window-based definitions of neighborhoods. Okay, so anything else is just as we've seen on the slide. So let's start already. We would perform the recursive computation. It would construct the table live. All right. We would access the result of this computation here, but we would confine our output to one specific generation. It talks about the configurable generation n here. Let's enter just one generation, for example, generation 3 here. And well, this string aggregate will just turn the XY encoding, the coordinate-based encoding of our grid into something that is readable again. All right, so let's do that. Let's look at the behavior here. Okay. Right, so that would be the state of the grid after 3 generations. And as you can see, oh, the rotor has indeed changed its form. It's not horizontal anymore. In this 3rd generation, it's indeed vertical. So horizontal, vertical, horizontal, vertical. Yeah, in the 3rd generation, it should be vertical. And I also think that these spaceships have moved or at least changed their appearance. Okay, right. So this is the implementation of Conway's game of life. Of course, the interesting behavior of such a dynamic cellular grid is only visible if we look at several generations in quick succession. So if we really animate the dynamic behavior of this particular grid, this query is prepared to actually do that if we let it compute the generation n of this of the cellular automaton of the game of life grid. Let me check. So n is not predefined here. That's fine. All right. So let's try to animate this behavior of the cellular automaton. I think that should be quite nice to look at. All right, so let's make this window smaller because we will be switching over to the shell here. All right, and what I brought with me is a shell script that's called Conway that I can supply with an integer parameter, and this means that this script will now invoke the PostgreSQL query with a generation n of 0 to display the initial grid. Then it will re-invoke the SQL query with a generation n of 1 to show the next generation of the grid of n of 2, n 3, 4, 5, up to 40. So we should be able to see 41 generations of the grid that that we have defined in our SQL code here. Right, so let's see whether we can see some interesting dynamic behavior here. Let's see. All right, so there you go. Indeed, we see the rotor behavior that we were expecting. From generation to generation, it just flips. And we see the 2 spaceships that are indeed moving along the grid here. So we are in generation 17, 18, 19 already. They are approaching each other, and I think they will collide any second now. They are colliding now, indeed. So now something chaotic happens. What will be the outcome of the 2 spaceships? Still behavior that is all right. Oh, okay, so we've reached this stable configuration now, and this will now reproduce until eternity. So, well, after 40 generations, there's nothing new to be learned here, and we are done with our simulation. That would be one run of the Conway game of life for the initial grid that we have defined over here in our SQL file. All right, so recursive queries can indeed simulate cellular automata, and this opens up an entire field of cool applications that we can grasp using recursive SQL. One such application is super interesting, I would say. It's the fluid simulation, and we will cover that in the next video. I hope you will be around when we do that. Until then, bye-bye.